Greetings all. Welcome to weekly science review organized by Vetri Labs. Here at Vetri Labs, we focus on implementing electrochemical technologies at scale. To implement anything at scale, you need to understand the fundamentals. And this is one way for us to get to the deep dive of fundamentals. We take an open access article in the field of electrochemistry. We all read for a week, and then one person leads the discussion, and then we follow on with Q&A and discussion. So you can also lead this discussion. If you are interested, please contact us at info@vetrilabs.com. Today's discussion is going to be led by Dr. Ayyappan Ilangovan. Dr. Ayyappan is a research scientist at Vetri Labs. Over to you, Ayyappan.
Thank you, Dr. Chok. Hello everyone. Today we'll be discussing about synthesis of dimeric molecules via silver catalyzed electrochemical homocoupling of organic bromides paired with electrooxidation of urea. So before going into, I would like to give a brief introduction about what is dimer and what is their importance. So basically a dimer molecule is formed by two oligomers that are joined together by either a strong or a weak covalent or intermolecular bonds. Basic dimer that we see is like glucose and glucose can form this maltose sugar dimer, where this is a homodimer because it's from the same compound, and whereas a heterodimer is a sucrose where glucose and fructose are combined together. So almost based on this dimeric molecules, they can have different symmetry, but the dimeric compounds with the C2 symmetry have been studied as a promising drugs for cancer treatment, HIV, Alzheimer, and other major diseases, showing like 1,000 times enhanced activity compared to their monomeric analogs. In addition, these bifunctional dimeric molecules are of very importance. It's bidentate ligands and applications ranging from catalysis to transcriptional activation of DNA. So what are the methods available for synthesis of dimeric organic structures? So you can, dimeric organic structures can be synthesized by using a transition metal catalyzed reductive coupling of organic halides or Ullmann reaction, or using an oxidative coupling of an in situ generated organolithium compounds with aryl halides, or you can use a photocatalytic coupling, or you can use an electrocatalytic coupling reaction. Among all these different methods, homogeneous transition metal catalyzed dimerization is the most convenient and efficient synthetic approach because it requires mild reaction conditions. But in practical applications, they are hindered because of their complexity of the catalyst and the additives they employ. And they are very sensitive to oxygen and water. And they also have toxic transition metal traces in your products, which gets difficult to remove. Whereas the Ullmann reaction or oxidative coupling of this or using this in situ generated organolithium compounds basically cannot be used for organic halides other than biaryls. So you have very limited options. So people want to switch to this more greener approach using photocatalytic. But photocatalytic coupling methods are in early development stage, and also the sensitivity of the photocatalyst to the presence of oxygen, and also the difficulty for the reaction scale up is the bottleneck for this approach. So there is a huge approach towards electrochemical synthetic methods because they are inexpensive and they are renewable and inherently safe route to reductive or oxidative synthetic organic chemistry. In general, electroreduction of organic halides to dimers rely on this dissolution of metal sacrificial anode. So basically on the anode reaction, you have a sacrificial reaction that's going through. So, but what happens is this negatively affects the atom economy of your overall electrochemical process. And this could relatively lead to the potential instability and can also cause cathode passivation by forming these magnesium halides. So on this study, they want to use the electrochemical approach of homogeneous coupling, but they want to modify this process rather instead of using this anodic reaction where you have metal dissolution, they want to use electrooxidation of urea as an anode reaction. So this group has previously done work on cathodic electrocarboxylation in aprotic media, basically the media without any proton. And they've paired it up with any oxidation process such as OER or urea electrooxidation in divided cells that are separated by an anion exchange membrane. In specific, this urea electrooxidation reaction is attractive in terms of both energy and environmental standpoints, because urea is the main nitrogenous base produced by humans, and it's also a major component of the wastewater from the urea production and dialysis industries. So treatment of urea is very essential to avoid its oxidation to nitrogen oxides, which is harmful, which has a harmful effect. So they extended this approach to cathodic coupling of organic bromides and studied its scope and limitations with respect to the structure of the organic substrate. So in specific, they have used cathodic coupling of organic bromides with electron donating and electron withdrawing groups paired with anodic oxidation of urea in aqueous media. So basically, they've used a primary benzyl halides or aromatic, aliphatic and aromatic halides. So a brief of their electrolysis procedure. So when they used a solution of organic bromide with 0.1 molar tetrabutyl ammonium bromide in acetonitrile as catalyte. And before electrolysis, they purged they saturated their catalyte with argon for 30 minutes with a flow rate of 10 ml per minute. And they also maintained the argon atmosphere during the electrolysis. And then an aqueous solution of 1 molar KOH with 0.33 molar urea with total volume of 14 ml was used as an analyte. And all these electrochemical reactions were performed at constant potentials that they saw in their CV. Then after electrolysis, the solvent from the catalyte was evaporated under reduced pressure. And then they added diethyl ether to the dry residue. So the insoluble in ether electrolyte was separated from the solution of the reaction products by filtration and then followed by the evaporation of the ether. So to analyze the formed product with they used NMR spectroscopy and then they prepared the sample by dissolving it in deuterated chloroform containing a known concentration of internal standard tetrachlorobenzene. And for the electrodes, they used a silver foil or carbon cloth supported nanostructured silver prepared by CVD as a cathode, and nickel foam was used as an anode, and silver wire was used as a quasi-reference electrode. Whereas in terms of two electrode undivided cell configuration, they used a silver foil cathode and a platinum foil or a magnesium foil was used as an anode. So first, let's see the cyclic voltammetry of their substituted benzylic bromides. If you look at in the figure A, you can see on the benzylic bromide 1A with a phenyl group and a methyl group. They both have like two reduction peaks. The first reduction peak is a cleavage of this carbon-bromine bond with the formation of this benzylic radical. And then the second reduction peak is a subsequent reduction of the benzylic radials to form this corresponding carbanion. So the first reduction peak of this benzylic compounds, the benzylic bromides, were observed at about minus 0.4 volt for both of these, indicating that they have the similar dissociation energies for this carbon-bromine bond. Whereas here you have a nitrile group, a methyl group, or a bromine and a fluorine group. For benzylic bromide with the nitrile group, the reduction peak at minus 0.27 volt appear only in the first two scans. Basically, if you look at their scan, this is the sixth scan, I believe, the dotted lines for the one with the nitrile group. This is the disappearing, they attribute that this is due to the nitrile because it's a strong electron withdrawing group that significantly lowers the potential of the benzylic radical reduction. to minus 0.5 volt compared to other substrates, leading to an overlap of your first and second electron transfer peaks, because you have your second electron transfer peak about minus 0.6 to minus 0.8 volts, depending upon which electron withdrawing or electron donating group you're using. And then the peak positions of the benzylic bromide 1 and 2 correlate with their electronic properties. For example, if you see for the one with the methyl group, because it's electron donating group, you can see it's highly negative potential. But as you have more electron withdrawing groups, as it gets stronger, the reduction peak shifts to a less negative potentials. And also on the one with for the one with the bromine, there is a presence of a reduction peak at minus 1.4 volt. This is a third reduction peak, and they attribute this to the reduction of bromine atom on the aromatic ring. Then they did the cyclic voltammetry for aromatic bromides. Here, compared to benzyl bromides, where you saw the onset potential at lower negative, here it's at high negative potential, because you have a higher dissociation energy for this carbon bromine mod that's shifting your onset potential to more negative. Then the reduction peaks were observed at potentials ranging from minus 0.1 to minus 0.13 volts. However, we don't see multiple distinct peaks as we saw for the benzyl bromides in case of aromatic bromides. And the reason is due to the less negative reduction potentials required for the second electron transfer step, where you produce this carbanion ion, compared to that for the one electron reduction of the initial bromide, where you form this bromide radical. So as the second reduction needs very small potential, the overall reaction seems to be spontaneous, and the overall process and the one reduction peak you get represents two electron reductive cleavage of this carbon bromine bond with the formation of corresponding aryl anions. And so all these cyclic voltammetry studies were done with the 10 millimolar solution that is in the present in 0.1 molar tetrabutyl ammonium bromide and 0.1 molar acetonitrate. And for aliphatic bromides, the onset potentials ranged from about minus 0.1 to minus 0.9 volts, depending upon the group you have. For example, when you have a formyl group, you have so the formyl is an electron withdrawing group in the alpha bromister. So adjacent to this C bond requires less energy compared. So that's why when it requires less energy, you have the onset potential at more like it's close to 0 volt. But whereas if this nitrile group or a formyl group is separated by an additional carbon atom, then you need a higher energy. So then that shifts the onset potential to minus 0.7 or minus 0.9 volts. And you can, as we see here, we can see two reduction peaks in the first few scans for all the three aliphatic bromides. This is basically, we can attribute it to the first and the second reduction step we saw like 2 slides earlier. However, when they run the CV after like six scans, and the sixth scan, they can see that there is a current decay is observed. And also you can see the disappearance of these reduction peaks they saw in the first scan. However, the current decay is not same for all the three aliphatic bromides. For example, if you look at the alpha bromister, the current decay was not significant, whereas for the B and C, the current decay was at least 6 times. And this is attributed depending upon the substrate. Because similar progressive potential shift and current decay were previously reported for other cathode materials such as glassy carbon, copper, and gold interfaces. So for bromides, for all these three aliphatic bromides, the formation of radicals is still possible at potentials that are close to the onset, and at more negative potentials, a 2 electron reduction process is expected, where you directly form this alkyl ion. So they did to see the yield for different products, like what is the dimer yield from different organic halides, they used the cell setup. And for comparison, they also used, so their approach is to use this divided cell where they have an organic catalyte and then a urea analyte, right? And they also, for comparison, they used this undivided cell with a magnesium sacrificial anode. So in the divided configuration, the anodic process is restricted to aqueous analytes because of the insolubility of urea in most organic solvents, while the cathodic organics in this require organic catalytes. So the electrooxidation of urea proceeds at the nickel-based anodes close to the water oxidation with a difference of about 0.2 volts. And closer to the onset, urea mainly oxidizes to nitrogen and carbon dioxide, while you can see contribution of oxygen evolution at more positive potentials. And the analyte did not significantly affect the cathode reaction at the cathodic potentials required for this RBR activation, even though if they can cross over because of the bromine ion. And specifically, a minor crossover of water into the organic compartment can resulted in a negligible amount of HER at the cathode. And also, they can the contributions of side reactions such as protonation of this electrogenerated radical by proton donor or hydrolysis of this RBR to ROH is typically observed only at very negative potentials beyond those required for one electron reduction. So, but in the undivided cell configuration with the magnesium anode, the major anodic process is oxidation of magnesium to magnesium 2 plus, followed by its combination with the bromine to form this insoluble salt. And this salt can either remain on your surface of the anode and block its active sites, or depart from the anode in form of small particles into the bulk electrolyte, which ultimately precipitates at the bottom of the cell or on the cathode, which can alter the overall performance of the cell. So those two electrode passivation pathways can lead to this instability of your current or cell potential. So overall, it will decrease your system efficiency. So then at this case, the potential magnesium 2 plus and can reduce to magnesium, which can further react with RBR to produce Grignard reagent that can lead to side reactions if you have any traces of water, or it can even from acetonitrile. So when you're operating undivided cell, you have a voltage restriction that you cannot operate it at a voltage higher than minus 2.38 volts. So then they did the long-term study for about 2 hours to see how the undivided and the divided cell performs. So a standard H cell equipped with a silver foil with 1 centimeter working area as cathode for both configuration, but for the anode, it was 0.5 centimeter square magnesium foil for the undivided, and for 1 centimeter square platinum foil as an anode in the divided cell configuration. And the cathode and anode was separated by about 5.5 centimeter and with the membrane placed in between the electrodes. As we can see on this plot, the cell voltage was in the divided configuration where we have the urea oxidation on the anode was very stable in the first hour of the reaction, and it only began to decline afterwards, which can be explained by this RBR concentration reaching a critical threshold for this cathodic reaction to become diffusion limited. In contrast, the operation of the undivided cell, we can see a rapid upsurge in the cell voltage from the beginning of the reaction, and its high instability afterwards can cause this considerable electrode passivation in this configuration. And also the initial voltages that they used in this galvanostatic experiments was determined by their electrochemical active surface areas of this metal foil electrodes, which can also be optimized by using nanostructured electrode surfaces. So then they evaluated what is the yield of the dimer based on the organic halide they are using. So first is electrolysis of this benzylic bromides. So all these reactions were performed at a constant potential corresponding to a current of 10 milliampere per centimeter square. These are normalized to the geometric area, with the catalyte is 0.1 molar tetrabutyl ammonium bromide with 0.1 molar organic halide in acetonitrile. Here its specific is benzylic bromide. And then the analyte was 0.3 molar urea and 1 molar potassium hydroxide. They did the experiment until they pass a charge of about 1 coulomb. Then this yield, and then they then they measured the yield. Basically, for one, which is the 2A with the nitrile group, their yield was was observed but only like 30%. So in detail, as you can see here, the reduction of all these benzyl bromides produce dimers with up to like yields starting from 85 to 100%, except the 2A. Because the reason is the yield, the 2A had a very significant yield of like very lower yield of 46%, and the byproduct had only 30% yield. The formation of RH correlates with the presence of the single peak, because as we can see on the 2A, there was only a single peak, and that indicated the competitiveness between this 1 and 2 electron reduction mechanism, because we have the presence of a strong electron withdrawing group, which is nitrile, right? That's why we saw those the reduction peak at minus 0.2 volts. After the first scan, it kind of merged together at minus 0.6 volt, having a single 2 electron step. Then the carbanion species participate in the formation of this RH, like organic halide, by the protonation of carbanion by proton donors. Also, they can react with the initial organic halide via this SN2 mechanism to produce the dimer. Next is electrolysis of aliphatic and aromatic bromides. So the reduction of aromatic bromides was evaluated the similar conditions as the benzylic bromides, with 100 millimolar concentration at a potential of about minus 1.4 volt in the divided cell. The formation of the dimer was not observed in all of the reactions, and only this had a yield of up to about 76%. These results, along with the CV data, shows that the reduction leads to the formation of this aryl species and not radicals, even at relatively lower potentials. And these forming reactive anions are not able to react with the initial aromatic bromide. So they come to a conclusion that this proposed approach is not suitable for the synthesis of biaryl structures. The biaryl is basically you have two aryl groups and like phenyl or naphthyl. And this basically, we saw initially that the Ullmann reaction is suitable only for biaryl structures, but whereas here it is not suitable for biaryl structures. And then they did the electrochemical reduction of alkyl bromides with a specific this 4B, where we had this formyl group under similar conditions, but the potential they used is minus 1.3 volts. According to the CV analysis, the electrochemical reduction of this primary aliphatic bromide should proceed mainly through the formation of this highly reactive anion species. And these species are very strong bases and nucleophiles that can participate in a variety of side reactions, or it can react with your aliphatic bromide via this SN2 mechanism to form your dimer. However, they found a yield of only 36%, and they were initially expecting to form an adipic acid, which is a precursor of nylon, but whereas they got only a dimethyl adipate, which is an ester of that acid, with a yield of only 36%. So as a result, they give what is the summary of the electroreduction mechanisms for different organic halides that they have employed. So for so the electrochemical activation of the organic halide starts with its adsorption on the electrocatalyst surface, followed by the 1 electron cleavage of this carbon-bromine bond with the formation of this adsorbed species. And for benzylic bromides, the electrogenerated radicals are stabilized by their conjugation with the aromatic system, and are relatively stable at the lower potential. And after getting desorbed from the surface, they can undergo a radical coupling to form the dimer. Whereas if the benzyl radical is bearing a strong electron withdrawing group such as nitrile, the electro-generated radicals are not stable and they can undergo further reduction to form the carbanion species that can react with your initial benzyl bromide to produce your dimer, or they can participate in the side reactions such as protonation of these carbanions by the proton donors such as water, acetonitrile, or your electrolyte. And for the aliphatic or the aromatic bromides, the formed radicals are very unstable and they immediately undergo one more electron transfer to form the corresponding aryl or the alkyl anionic species. And based upon this, the aryl species can further react with the hydrogen donor present in the solution to form RH as a major product. In contrast, um, besides reacting with hydrogen donors, these alkyl ions are basically strong bases, so they can react with the starting aliphatic bromide by this SN2 mechanism to form the dimer. So in summary, they proposed a simultaneous electrochemical coupling of organic bromides and aqueous electrooxidation of urea in divided cells. This is in contrast with the traditional one compartment cells with sacrificial anode. The proposed configuration relies on a sustainable anodic process and enables maintaining a stable cell potential for about 1 hour when they do the constant current electrolysis. And based on the CV results, we can see the onset potentials and peak positions showed a strong dependence on this organic substrate structure, specifically on the carbon-bromine dissociation energy and the redox properties of the formed radicals. The electrochemical reduction of benzylic bromides proceeds at a relatively lower potential through the formation of radical species and yields the target dimers with yields from 85 to 100%, with the exception of benzyl bromides bearing strong electron withdrawing group, whereas the yield was only 45%. In the case of benzyl bromide, the reduction proceeds the formation of anionic species and the dimer is formed with moderate yields. Electrochemical reduction of aromatic and primary aliphatic bromides proceeds exclusively through the anion species. For aromatic bromide, only RH product is formed, while for aliphatic bromide, dimer is produced with low yields up to 36%. With further optimization of the reaction conditions along with transition to a flow reactor, they predict that this approach can be scaled for sustainable coupling with the simultaneous electrochemical treatment of the nitrogenous waste. And thank you all for listening, and we can move to the discussion.
Thank you, Ayappan. That was a very nice summary. So, my first question that came up to me when I looked at this is they were attributing the second hour of increase in voltage to diffusion limitation. But I was wondering about the electrolyte mixing because there is a concentration difference of the aqueous species as well as organic
Okay.
species, right, across the membrane.
Yeah.
They do comment on anything on that, how much of the electrolyte intermixing is happening, or maybe there's some diffusion of one species to the other and that impacting the performance?
No, they say even the analyte going to the other side, or they are, for example, if the bromine ion comes in, they say the bromine doesn't affect the reduction because the reduction of the bromine ion needs a very high negative potential. So they say that they don't the crossover of the electrolytes does not interfere with their electrochemical results that they observe.
So I can think of the electrochemically active components are not interacting, but how about the ionic conduction path because of the mixing?
Yeah, they haven't commented on those.
Okay, got it. Others, Ramesh, Sriram, Raghu, any questions, comments?
I don't have any questions much.
Okay.
Yes, it's a bit new for me. And only thing is they coupled aqueous and non-aqueous system together. And whatever you asked, the mixing of electrolyte, it will be a drastic one. It cannot be a simple one. So they didn't notice that one in any case. And still they were measured the potentials on what basis they have mentioned with respect to SHE, that I'm still wondering how they were representing with two dissimilar electrolyte system and countering with SHE, finding the potential. Still that one question
Yeah.
is there for me.
Yes, separation of ohmic contribution versus the mass transport. I don't know. I don't believe they did any AC impedance. I didn't see it in the paper to understand if it's mass transport or not.
Yes, they did do. They have not. Maybe it might be there in the ESI.
Right. I didn't see that. Right. Ayyappan, did they do
Yeah,
any?
no, they didn't have any supplementary information with other data. No.
Got it. Got
Oh,
it. Yeah. Okay. What was your observation, Ayyappan, other than the summary, like from your point of view? What did you feel about the paper?
From my point, I thought it was more towards like how the products like were changing, like what is the yield and everything. But I thought there was less electrochemical interpretation of their results, like rather than just observing the voltage. That is what they've done. But they probably did. I mean, I think they were probably more organic chemistry based. So they did the reaction mechanism. They were able to see how the mechanism can proceed, and what are the and also I wasn't sure how they commented on the side reactions, because I don't see any like proof that they have given that the side reactions has not been common apart from just taking, because they had a lot of literature citation.
Okay.
All their comments or conclusions, they said we don't expect this to react, or we don't expect the traces of water to contribute and those things. So
Got it. Got it. Okay. Okay. Great. Thank you. Ayyappan, what are we talking next week and who's talking?
it's me. So the topic is electrochemical reduction of CO2. So that is one of the major topic for the throughout the world. So
Yes.
that's what I was concentrating now.
Great. Looking forward to that, Dr. Ramesh,
Yes,
next
yes, sir.
week. So you can also join us either live or you can listen to it in the recorded version. If you'd like to lead, again, the email address to contact us is info@vetrilabs.com. Thank you for joining us. See you next week.
Thank you.